Now, welcome to a lecture, Fact and Power Quality. In the previous lecture, it has been discussed that if the transmission line consists of only reactance and there is some voltage and kilometer length of the line is going to consider what are the limitation of EHV transmission line over the say HVDC transmission line. In the previous lecture, we come to know one formula that the power is equal to P is equal to 0.5 E1 E2. If E1 and E2 is equal to same, means sending end voltage and receiving end voltage is same. Definitely 0.5 E square upon L into X, where L is the length of transmission line in kilometer and X is the reactance of transmission per kilometer. So this much power can be handled, or this much power can be transmitted from sending in station to the receiving end station in megawatt. So this table is shows that this is the system voltage 400 kV EHV transmission line, 750 kV transmission line, 1000 kV transmission line, and 1200 kV transmission line, where on the column wise this is 400 kilometers, 600 kilometer, 800 kilometer, 1000 and 1200 kilometers, and this much is the power handling capacity in megawatt. It means that if the voltage of transmission system is 400 kV, okay, and length of the transmission line is 400 kilometer, it may transmit up to the 670 megawatt. Okay, whereas if the system voltage has been increased to 400 to 750 kV, the power handling capacity of the transmission line get increased by nearly 4 to 5 times, that is 2860 megawatt. Similarly, if the transmitting voltage of the system is 1000 kV, the power transmitted nearly 10 times, and similarly for 1200 kV transmission line, the power handling capacity is going to increase by 12 times with respect to 400 kV transmission system. So the simple conclusion is that if you increase the system voltage, the power handling capacity of the transmission line get increases of, it may be a 4 times, 5 times, or 12 times are there. But if the length of the transmission line increases, say it is from 400 to 600, earlier the power transmitted by the transmission line is 670 megawatt, it is decreased to 450 megawatt. Similarly, corresponding to 800 kilometers, the power transmitted again reduces to 335 megawatt and so on. So up to the 1000 kilometer, the power transmitted or power handling capacity of that line is reduces to 270 megawatt. Similarly, for all the voltage level, the same 6 situations are there. Say for example, 1000 kV transmission line, 600 megawatt, 6000 megawatt, and it is up to the 1200 kilometer, it is only 200 kilometers are there, isn't it? So this is the case in the power handling capacity of the transmission line. Now in India, we are having 400 kV transmission line and one more line 765 kV, which is laid between Chandrapur to say one nearby area. I just remembered, I just forget the name. Okay, so but if you increase the system voltage, there is some electromagnetic effect over the human being as well as say infrastructure. It will create some disturbance in the communication system, and the human being as well as animals, those are grazing under the transmission line, it develops some static charge, and therefore there is some in view of this biological effect, we are not going toward the higher voltage transmission line. Because of this limitation of EHV transmission line, as the length of the transmission line increases, the power handling capacity of the transmission line decreases. And why it is so? It is because of the reactance of the transmission line. As length increases, in this formula, see here, in this formula, if you just see the, if you just see the power is equal to 0.5 E1 E2 divided by L into X, where L is the length of the transmission line and X is the reactance per kilometer of the transmission line. So this denominator factor increases with increase in length, and hence the power handling capacity of the transmission line also decreases. So in view of this limitation of EHV transmission line, in the previous lecture we have discussed that our generation is from the east region, and whereas the load pockets in the western region. Similarly, the coal mines which is available in say what we can say that it is the Bokaro and all this area, it is quite difficult, and it is not economical to erect the thermal power plant in nearby to the load center and transmit the coal from the western region, or maybe from Chhattisgarh, or from this region, say Bokaro and all this, to transmit the coal and generate the power near to the load center. So it is quite, it is not economically feasible, and it is not advisable. So what we are doing, we are erecting the generating plant in that area where coal mines and natural resources are there, and with the help of transmission line, the power is going to transmit. Only one difficulty is that whatever the amount of power is generated, it cannot be transmitted. Whole amount of power cannot be transmitted to the load center because of the some constraints. And these constraints are the transmission line constraints. First is the first is the thermal stability, depend upon the full load current, ambient temperature, and geographical condition of the transmission line. Second is the stability. Stability is the one is the steady state stability, transient stability, and dynamic stability. And next is the say what we can say that it is depend upon the dielectric strength. Dielectric strength is nothing but we can say that there is a, if you are increasing the system voltage 400 kV to 750 kV, definitely we have to use some different type of insulating material, and which may not be available, and hence it will play a very important role in the constraints or some limitation of the transmission voltage. Okay, so under such condition, FACT devices or the use of FACT devices become a very attractive solution to avoid this loss in the transmission line. Means loss in the transmission line, it means that whatever the amount of power going to transmit generated, it cannot be transmitted, or it cannot be evacuated effectively to up to the load center. So with the help of FACT devices, it is possible to modify the electrical characteristic of existing transmission line, and hence the power handling capacity or power transfer ability of the existing transmission line can be enhanced. So objective of FACT devices is to enhance the power handling capacity of the existing transmission line, reliability, reliability, as well as the improvement in stability point of view. So these are the major say objective to use the FACT devices, isn't it? So FACT devices are going to control the transmitting line parameters like voltage, current, its impedance, isn't it? Either by injecting the voltage in series or injecting the voltage in say in quadrature, which you see one by one. So this is the objective of FACT devices. So what is the opportunity? The opportunity is such that the FACT devices can be connected to the transmission network in many ways, such as a series. So it is called as a series FACT devices. It may be connected in shunt or the combination of series and shunt. So either we can connect this FACT devices in the series, of the transmission line, shunt in the parallel, that is a parallel in the transmission line, or combination of both. And that fact devices is controlled either by it is what we are doing. We are controlling the impedance of the transmission line. So definitely either we have to insert some capacitor or some inductor to vary the impedance of the transmission line. So it is a thyristor controlled a series capacitor or static synchronous series compensators are connected in series, and it is a static VAR compensator. Similarly, the fact devices can be connected in shunt, that is called as a synchronous compensator or statcoms, to improve the voltage profile or maintain the reactive power. Or sometimes they are coordinately controlled, that is a series as well as shunt devices. They are controlled they are controlled unified, means coordinately connected to each other to control the active power. So these are the opportunity of fact devices. So opportunity of fact devices, or the objective of fact devices, is to enhance power handling or power transferability of the existing transmission line. Okay, since our generating stations are far away from the load center, and to maintain the reliability and economic point of view, all generating stations, they are connected to each other to form a grid. So this is the objective of interconnected power systems and interconnected power system and use of fact devices. Now, what is the world scenarios? The first SVC, static VAR compensator, for the utility application was installed by the General Electric at North America in 1974. Means the static VAR compensator, or the type of some introduction of fact devices, has been introduced in year 1974 by the General Electric. So you know that General Electrics and Westinghouse industry is very famous say industries and organization in the electrical field, electrical engineering field. Further, some installation of the fact devices in America as a TCSC. It is a thyristor control series capacitor. We are using the electronics thyristor family to turn on and turn off these devices, and it is a series compensator, rating of 202, means 202 MVAR at slat 500 kV substation, isn't it? So these are the some say initiation, or say it is the penetration of these new devices in the existing power system. Now, India. In India, it has a definitely opportunities. Fact devices has opportunities. The reason is that our most of the power plant is from the eastern region and the load in the western region, and therefore we have to transmit the power at a long distance from, it may be from Chandrapur to Mumbai or Pune, like that one. Similarly, from Chhattisgarh area or some Bihar, Bokaro, and from where the coal mines or coal pits are available. Therefore, whatever the thermal power plant, because in India, nearly 66% are the thermal power plant, and thermal power plant play a basic role of the, say we can say that it is a base load power plant, and therefore power has to be transmitted from a long distance. And when the EHV transmission lines are there, extra high voltage transmission lines are there, definitely with increase in the length of the transmission line, power handling capacity or power handling capability of the transmission line get decreases. To improve that power handling capability of the transmission line, we are using the fact devices. So in India, fact has received much attention in the last 2 decades, that is nearly 20 years. The first fact device installed in India as a thyristor control series capacitor with fixed series compensator at 400 kV transmission line between Kanpur and Balaghat. isn't it? It is in the Haryana, in the northern grid. Say, no doubt in America also, the first FACT devices is the TCSC, because it is a series compensator. TCSC is the thyristor control series capacitor. The series capacitor rating, the need of series capacitor FACT devices is that the MVA rating is small. So as per cost point of view, the cost of series compensator is smaller, isn't it? And it controls the active power also. So therefore, the fact and it increase the power handling, or say power transferability of the transmission line. That has been explained in the last lecture, how we can improve the power handling capacity of the transmission line. Say a very basic example or basic concept is that if the reactance of the transmission line decreases, either by a parallel transmission line or by bundled conductor in a transmission line, definitely the total equivalent reactance get decreases, as the reactance in denominator for the power handling capacity or power handling equation, which improve or enhance the power handling capacity of the transmission line. So TCSC also decreases the total impedance of the transmission line, hence it improves the power transferability of the transmission line. Okay, so this is the first. Some more existing FACT project which was successfully installed in India are Rachi 400 kV DC means here it is a double circuit line, that is a 370-kilometer transmission line with 40% FCSC. What is the FCSC? It is the free fixed series compensator. At Rachi and Raipur Raulkela 400 kV transmission line, double transmission line, 412-kilometer line with FCSC, that is a fixed series compensator and thyristor control series capacitor installed at Raipur. So why we are using this capacitor, this series compensator in that area? Because it is a cluster of generation pocket, and we want to transmit bulk amount of energy, bulk amount of power from cluster of generating area to the cluster of load area. Okay. So these are the some of the FACT devices also installed in Andhra Pradesh. So these are the present scenario in India and opportunity of FACT devices in India. What are the proposed FACT projects in India? In Maharashtra, it is at 220 kV transmission voltage. The estimated cost for the FACT devices is 57.75 crore. Similarly, in Jammu and Kashmir, again it is a 220 kV transmission line, and the rating, the MVA rating of the FACT devices, it may be a shunt and series, or it may be a combination of shunt and series, is 125 MVA. And again it is 57.75 multiplied by 2. So this much is the amount for the FACT devices, or there is a proposed project for the to improve the power handling capacity of the existing transmission line in India. Similarly, some of the in Andhra Pradesh, Karnataka, Rajasthan, and Gujarat, all at level of 220 kV, and there is a total cost is proposed cost or estimated cost of the project for Statcom and FACT devices is 704 crore rupees. So these are the some proposed project in FACT devices. Again, some controlled reactors projects are there in India also, which is installed at Busbar, means near the substation. That is in Tamil Nadu. It is 420 kV transmission line. In Kolhapur, there's a 765 kV transmission line, and somewhere it is 765 kV transmission line. That is has been explained that we have installed some 765 kV transmission line, but it is very few places are there. So in Maharashtra, in Kolhapur, 400 kV transmission line whose capacity is 400 MVAR, and similarly in Tamil Nadu it is a 400 MVAR capacity, and the estimated cost is 211.75 crores. So no doubt the cost of the FEC devices is very large, but it is the initial investment, and the regular benefit is that the bulk amount of energy can be transmitted from generating station to the load centers. Now we'll see the summary of this discussion. The summary of discussion is that right from the what is the need of interconnected power system, then what are the different stability issues related to the EHV transmission line, power handling capacity of the transmission line, and opportunity of FEC devices. What is the basic FEC devices are there? So it is found that the power systems are interconnected to ensure the reliability and economy, no doubt. Whatever the number of generating stations, right from a 5 grid to it become a 2 grid in India, or it may be a single grid in India. The objective of this interconnected or single grid in India is to ensure the reliability of the system and power security in the system, isn't it? And second is the economy, because in India there are different type of generating stations. It may be a thermal power plant, hydropower plant, wind power plant, solar power plants are there. The cost of generation become economical or feasible only when as already you have learned in the power system operation and control, or it may be a economical dispatch, economical consideration of the generation, when lambda, that is the incremental power cost of all generating station become same, the cost of the generating energy will be economical. So this is the first point. Second, reliability ensure that the loss of any element has a minor impact over the system operation. No doubt, if a single generator supplying power to the local area, suppose the Deepnagar is supplying power to the Jalgaon district or say Dhulia districts over this one, if there is a failure in the system or there is a even a small impact in the system, it is going to observe throughout this region, isn't it? And there may be a power loss, there may be a blackout. But if you are connecting the different generating station together, the power is going to transmit by the next nearby generating station, and it maintains the reliability and continuity of supply. At the same time, whatever the impact over the system, it is going to spread over the interconnected system, and we can observe a less or sometimes we never observe any say loss of power, or there is a impact of system in our user end, isn't it? So the reliability ensure that the loss of any element, that may be at one transmission line, one generator get tripped, it is not going to impact over the system. So this is the second advantage of interconnected system. Interconnected power system can utilize the economic associated with large power plant as to oppose a many small one, isn't definitely. If you are using a small generating station everywhere, independent, definitely in the night time the generators are going to load at its lower value, so it does not give the proper efficiency, and in the daytime the generator get loaded or it may be overloaded. But if you are connecting the all generating station, we can do a proper coordination between a different type of generators, different capacity of generator, in such a way that all generating units may operate its economical loading, economical percentage loading, and hence it will give the economical operation and full use of infrastructure. Also, diversity in the time of peak demand within the grid ensure that the total peak demand is less than the sum of peak demand. It is very important because the peak demand is different for the different region. For the agriculture sector, the load increases in the night time as per uh, uh, new methodology. We are supplying three-phase power to the agriculture sector in the night time, where in the daytime industries and offices are going on. So the load is going to vary in the daytime. So if you are connecting the all generating station together, the maximum demand on the generator is smaller as compared to the individual generator operator. So as the maximum demand is smaller, definitely it means that there is a diversity and load factor of the generating plant will be small. As the load factor will be small, it means that the load curve become as flat as possible, which ensure economical generation of the system, isn't it? Now, next is the practical power system and opportunities for the FACT devices in our country is studied as explained. We have come to know what is the use of FACT devices, what is the objective of FACT devices, and depend upon the FACT devices, what are the say opportunities and scope of the FACT devices in India. So this is the some basic one regarding the say FACT devices. Okay. Now, next topic is that what is the basic type of FACT controller and symbol for the FACT controller. Basic FACT controller is a basic type of FACT controller. Before going to basic type of FACT controller, we have to understand some discussion. In general, the FACT controller can be divided into the four categories. These four categories are series controller, means the FACT device which is connected in series, it is called as a series controller. Second is the shunt controller, it is connected in parallel or at near to the load, or it may be a midpoint of the transmission line or from the sending end. Combined series controller, where two series controllers are connected in two parallel transmission line. Either it may be independently controlled or coordinately controlled to each other. Similarly, combined shunt and series controller, where FACT devices which is connected in series and shunt, it is coordinately controlled each other. So this is the basic diagram for a series controller, or this is only this one is the FACT symbol, as it is connected in the transmission line in series. Therefore, it is called as a series controller. A series controller could be a variable impedance. No doubt, our objective to control the parameter of transmission line. And what is the parameter of transmission line? Is the impedance. So by controlling the impedance of the transmission line, it is possible to enhance the power handling capacity of the transmission line. So series controller could be a variable impedance such as capacitor or reactor. It may be a reactor, it may be a capacitor, which is a variable one. And the varying of this inductor and capacitor is done with the help of electronic based variable source of maybe in main frequency. It may be or at sub synchronous frequency. You can call as a harmonic. So it is going to control the harmonics also to serve the desired need. In the principally, it is all series controller inject the voltage in series with the line. So this is a very important line. What is that? All series controllers inject voltage in series with the line. So it is injecting the voltage in series with the line. Even variable impedance multiplied by the current flow through it represent the injection of series voltage. What it means? A current multiplied by the inductor is nothing but the voltage. As this voltage is injected in series with the voltage, in series with the transmission voltage, therefore you can say that series compensator is a voltage injecting device, isn't it? And when it is voltage injection device is there, definitely it enhance the power handling capacity of the transmission line and also some sort of voltage profile. Okay, so this is the series compensation. Okay, as long as the voltage in phase quadrature means it is 90 degree with the uh, line current, the series controller only supply or consume variable reactive power. Try to understand one more, I repeat it. As long as the voltage in phase quadrature with the current, suppose this is the current is there and the voltage in phase quadrature, that is in 90 degree. Either it may be lagging side, it may be a leading side. When the voltage and current, they are 90 degree to each other, it deals only the reactive power. Either it may be a leading reactive power or it may be a lagging reactive power. So as long as the injected voltage in phase quadrature with the current, the series compensator supplies or consume variable reactive power. Any other phase angle means in between the 90 degree, less than 90 degree, it supplies or consume reactive power as well as active power. So by controlling the injected voltage, if it is 90 degree with respect to the line current, it is used to control the reactive power in the transmission line. Whereas when the injected voltage in between 0 to 90 degree, it deals active power also. So this is the meaning of series controller or series compensator. So for today's lecture, it is okay. And next time we'll see what do you mean by shunt compensator.